All right, everyone, thank you so much for joining for what is now our fourth seminar in our virtual seminar series on Gaussian processes, spatial temporal modeling, and decision-making systems. I'm so excited to have everyone here. Thank you so much for joining. My name is Jeff Pleiss, and I'm a postdoc at Columbia, and I'm one of the organizers who's going to be hosting today's event. I'd like to thank my other fellow organizers. We have Alex, we have Lisa, and we have Ji, who have helped to put this series together. And we're really excited about it. And so again, yeah, thank you so much for coming. Before we begin with today's talk, I would like to make just a few organizational announcements, which you've probably heard if you already attended some of these earlier seminars that we've had. So first off, following this keynote, we've got an amazing lineup of speakers for the remaining weeks. So please check out our website. It's gp-seminar-series.github.io. I will go ahead and put that link in the chat right now. So if you haven't checked out this website already, please check it out and see the other amazing talks that we have lined up, and see some of the videos of the talks we've already had so far. You can join the seminars via Zoom, as some of you might be doing already, provided you register to receive emails with the links, which can be done at the website. You can also join the seminars via YouTube, which does not require registration. Seminars are going to take place at 1600 UTC, that's Coordinated Universal Time. And note that your local time may change due to daylight savings, so please be on the lookout for that. Finally, for those of you who are joining via Zoom, if you want to ask questions during the talk, you can use the Zoom's raise your hand option to ask questions or type them in the chat. Shengyang has said that he is happy to take questions during the talk or also at the end of talk, so whichever you find to be more preferable. And with that being said, it is my pleasure to introduce Shengyang Sun, who is going to be giving our talk today entitled Structured Interdomain Inducing Points for Variational Gaussian Processes. So Shengyang is a PhD candidate in the machine learning group at the University of Toronto. And his research focuses, amongst many things, on Bayesian machine learning, including Gaussian processes and Bayesian deep learning. And he aims to leverage Bayesian probabilistic methods to improve the quality, reliability, and efficiency of machine learning systems. And with that, Shengyang, the floor is yours. Please feel free to start your talk.
Thanks, Jeff, for the introduction. Can everyone see my screen share here?
Yeah.
Yeah, thanks. Yeah, so I'm very excited to be here today to give some, to talk about some works on my past years. So in particular, I'm talking about structured interdomain inducing points for variational Gaussian processes. So, and a brief outline of today's talk will be starting as a background section that's introducing the standard interdomain inducing points and the particular variants, the variational Fourier features. And then I will talk about two projects. One is harmonic variational Gaussian processes, where I design interdomain inducing points to achieve computational savings in variational GPs. And second project I'm talking about is about interpreting neural networks using the technique of interdomain inducing points. So, and let's get started. So since we are doing a GP standard, so I will go very quickly about the standard foundations of Gaussian processes. So intuitively, a GP can be seen as a natural generalization over a multivariate Gaussian distribution. In particular, its prior model defines that the function values at any finite locations has a multivariate Gaussian distribution with a mu usually set as 0 and with a kernel matrix. And the kernel matrix usually is more important, lies in the central role of a Gaussian process. So Gaussian process is so intriguing because it has very good property that under a Gaussian likelihood, the GP posterior can be computed analytically. It has an explicit form expression as shown in here. So although it is appealing to have this analytic expression, it also raises the caveat is that we need to do the matrix inversion here, as you can see. But matrix inversion, the matrix here K is of the size of n by n. N is the number of training data sizes. So it's really hard to, or it's kind of like impossible to support this cubic computation to the number of data set size. Especially imagine that you have a data set with 1 million data points, so this posterior will be intractable. To overcome this obstacle, the technique of inducing points has been proposed and developed. In particular, inducing points, usually denoted as Z, are a small set of points trying to summarize the whole data set and used in variational GPs. Here I denoted like VGPs. So here is a simple example I took from the Latimer paper that imagine that we start from a large data set, and here each black dot represents the training data points. And variational GP will start with some initial training induced points, and I'm initial training induced points initialized here. And you know that at generalization, this induced points is not really representative of training data because it's located in a narrow region here. But the variational GPs give us a principled way to optimize the locations of inducing points. And after maximize the evidence lower bound, we can have the conversion induced points. And you can see that it finally be more representative and characterize the training data well. And when we use this conversion induced points, we can compare the variational posterior and true posterior. We can see a perfect match or accurate match here. So it gives us good posterior approximation with the manageable complexities. In particular, the computational complexities is reduced from n cubic to m cubic, when n is the number of training data and m is the number of inducing points. Imagine that we can use 1,000 inducing points, and this computational cost is totally manageable. So to understand more with the technique of inducing points, let's look at what, when we're optimizing the inducing point Z, what we are really optimizing for. So when we have a GP model, we already, and the training data sets, or maybe a larger data set, points X, the kernel matrix KXX is already fixed. Here I'm showing in the color, gray color. But when we optimize Z, we actually, what we're doing is trying to optimize the matrix KXZ, KZX, and KZZ under the constraint that the overall joint kernel matrix is always PSD. So therefore, we wonder, instead of purely optimizing Z, can we do something more direct? Can we directly optimizing the matrix B transpose, and C under the constraint of the augmenting kernel matrix is PSD? Actually, this can be directly done as seen in the formulas of the variational GP. So as long as we can augment the original kernel matrix into a bigger one, and then we can use a variational Gaussian process without the need of a standard inducing point approach. So this sounds very appealing, but it's also very difficult because the PSD property of a kernel function is not very easy. So how to design PSD augmented kernels? That is the question. And interdomain inducing point basically gives us an answer. So interdomain inducing points stands on the relationship between the kernel and the stochastic processes. So in particular, if we have a stochastic process fx, then we can compute its covariance between any two locations, x and x prime. So this will get us the post PSD kernel kxx prime. And interdomain inducing point trying to use this concept to build or to augment the stochastic process. In particular, it starts from any function W. So here W is a function from the input domain to a real space. And given this function, we define an inducing variable using this stochastic process. In particular, as we can see, the inducing variable use of UW is the integration of fx and with wx. We know that the UW also is the integration is actually the linear operator of fx. So if f is a Gaussian process, the UW is also jointly Gaussian with fx. And we can also compute this augmented covariance between fx and UW. So with some integration formula here that we, so basically under expectation, the fx becomes a kernel function. So if you have two inducing functions, W and W prime, then we can also compute the covariance between their corresponding inducing variables, UW and UW prime, as shown in such a format here. So now we can compute covariance between for this augmented stochastic process. So it naturally gives us a way to augment the original kernel that is defined only over the input space, now over the input space together with any function space, as long as the integrations are well defined. So therefore, we augment the kernel to be between the input x and the inducing function w, and also between any two inducing functions. And showing this diagram, we can augment the kernel matrix in such a formula. So this is a standard approach to augment the kernel matrix via a bigger one that is also PSD. And in particular, variational Fourier features is another type of interdomain inducing points that gives another way to augment the kernel matrix. It stands on a similar concept for the connection between kernel and the stochastic process. But a variational Fourier feature actually established the inducing variable in a different way. So given any function w also from the input space to the real space, the inducing variable is not defined as the inner L2 inner product between the fx and the weight function w. Instead, it's defined as the RKHS inner product between f and w. We know that it's because more complicated, but still it's a linear operator. It is a linear operator, then if f is already a Gaussian process, then UW is still jointly Gaussian with f. Therefore, we can still compute their covariance. There's something interesting happens is that when we compute the covariance between fx and UW, it's equals to the RKHS inner products between the kernel function kx and the inducing function w. And if you're familiar with the kernel methods, then this is the reproducing property, and it can be directly equals to the wx, the evaluation of w on the point of x. And there will be something very interesting and will be very useful when we introducing the second product. And similarly, we have two induced functions, w and w prime. We can compute their covariance. After some mathematical manipulations, we can show that it equals to the RKHS inner products between w and w prime. And all this are under the assumption that all these integrations inner products are well defined. So the variational Fourier features then give us another way to augment the kernel function, and we still denote it as kxw, kw prime. And for the diagram, it says it has a simpler formula. So imagine that we have the data set x, we have a set of induced functions, maybe m inducing functions written as uppercase w, then the kernel function between them will be w evaluated on x. And the kernel matrix between these inducing functions will be the inner product between any pairs of the inducing functions. So now we have two ways, a standard interdomain inducing points and a variational Fourier features to go beyond the standard inducing points. But why do we care about it? So here I briefly talk about three reasons about the applications of the benefits from these approaches. So firstly is that it can enable accurate posterior inference. As previously has been demonstrated, the quality of GP posterior inference is tightly close related to the quality of next term approximation using these inducing variables. And now we have the interdomain points, which is a more flexible way to build in inducing variables. So they might give us a more accurate next term approximation and a more accurate posterior inference. And secondly is computational benefits. So when we're dealing with standard inducing points, maybe we are using an RBF kernel, the computational bottleneck in a variational GP lies in the cubic computation of the kernel matrix KZZ. But if we can design the interdomain inducing points very carefully, it might turn out that kernel matrix for the inducing variables KWW becomes a structure. Maybe it's the block diagonal, maybe it's even diagonal, so that we can have a lot of computational benefits. And lastly, it might, because it is really a generalization and extension of the standard inducing points approach, it gives us a wider applicable scenarios of kernel methods. And in the next, I'll talk about two projects. Now, one project, the first project on how do we achieve computational benefits using interdomain inducing points, and the second project talking about how do we enable the kernel, a wider applicable scenarios of kernel methods to understanding neural networks. Okay, so let's get to the first product, the harmonic variational Gaussian process. So to talk about this product, I will start with a very simple example, although it might involve a little bit of math here. So basically, this simple example start from defining two interdomain inducing functions. How do we define them? We start from two inputs Z1 and Z2. So Z1 and Z2 are from the input space, maybe like the two locations, Z1 and Z2. We define two interdomain inducing functions, W1. As we can show here, W1 is concentrated on two direct masses. So W1 is a function that's only concentrated on two locations, Z1 and minus Z1. And we do an average here. Similarly, W2, the inducing function, is also concentrated only on two locations, Z1 and minus Z1, but we take a minus here. So we know that W1 and W2 are two functions, inducing functions, and sometimes I'll just call inducing functions also as interdomain inducing points. So I will use them interchangeably. So it's very interesting that if we can compute the augmented kernel function for these inducing functions. In particular, we can compute the augmented kernel value between W1 and W2 as such an integration. So basically, this integration is a kernel function times the W1 times W2 and do integration. But note that the W1 and W2 is full of direct masses. So we are always happy when we find that there are direct masses when we are doing an integration. And it also happens because this can be directly written as the linear operations of four terms, because there's only four terms, four direct masses. And in particular, I'm showing it in two colors, KZ1, Z1, minus K minus Z1 minus Z2, and Z1 minus Z2 minus Z1, Z2. So why is this interesting? We put another additional assumption is that if the kernel K is invariant to negations. What does it mean? This means that if the kernel K for any two inputs, if we negate the two inputs X and X prime, their kernel values are the same. We know that a lot of kernels are commonly used are invariant to negations. For example, the RBF kernel, because it only depends on the Euclidean distance between the two inputs, and we do a negation, the Euclidean distance is preserved. So the kernel is invariant. Also for linear kernel or polynomial kernel, that only depends on the inner product between two inputs. And when we do a negation, the kernel value is also preserved. So a lot of kernel are invariant to negations. And if the kernel K is invariant to negations, what do we have? We have that W1 and W2, their kernel values is 0, because we can initially see the green terms canceled and the red terms cancel each other. And that is the interesting thing, is that for any Z1 and Z2, as long as we define the W1 in such a form and W2 in such a form, their kernel value will be 0. So what do we have for that? Then we have a 2x2 block diagonal kernel matrix for the inducing variables. In particular, imagine that we have lowercase m, we have m inducing functions of the first type, as shown here as the uppercase W1, and we have m inducing functions of the second type. Here, for simplicity, I'm just seeing m and m are the same, but you definitely can vary using different m here. So we know that the kernel matrix between the inducing variables is 2x2 block diagonals. The cross terms of diagonal are always 0, as we have already proved before, under the assumption that the kernel is invariant to negations. And this will bring us computational benefits, because now we can use 2 times of inducing points with only 2 times of computations. We know that in a variational GP, the computational bottleneck is the inversion or class C decomposition when we're dealing with kernel matrix, that is m cubic. But now we can use 2 m inducing points with 2 m cubic instead of 8 m cubic. That is where the computational benefits comes from. And this is very intriguing, but not good enough. We wonder, can we do better? Now we have a 2x2 block diagonal. We always wonder, can we do like a T by T block diagonal or even a diagonal matrix? Then that will give us huge computational benefits. Actually, it is something that we can do, as we show in this paper. So to generalizing this simple example, I'm showing let's look at what the key ingredients in this simple example that make the orthogonality works. So firstly, it involves a negative transformation, the negation. The negation maps x to minus x or z to minus z, and also maps minus x to x. This is the negative transformation. We also assume that the kernel is invariant to negations, i.e. in such a form. And most importantly, we define two types of inducing points or inducing functions. The two types of inducing points has this previous formula, but we can write it in a compact way in the matrix. So here the 2x2 matrix, and each row represents one type of inducing points. Like for example, the first row represents the average of the two direct masses, and second row represents the subtraction between the two direct masses. So now we have two types of inducing points, and we can do the generalization to generalize to arbitrarily t types of inducing points. Correspondingly, a negative transformation becomes a t-cyclic transformation. What is a t-cyclic? Basically means that we have the transformation g. If we apply g for t times, then we get back to the original point. For example, here I'm showing a g that is a 90-degree rotation. If we do the 90-degree rotation for 4 times, it gets back to the original x. That is a 4-cyclic transformation. And similarly, we require the kernel is invariant to g, and instead of do the negation, we do the for any two inputs x and x prime, applying the transformation g, make this invariant. And finally, most importantly, is that how do we generalize this matrix representation? We observe that this simple 2x2 matrix actually equals to the discrete Fourier transform matrix when we are doing a Fourier transform for only 2 time steps. So imagine that we have a sequence with only 2 values or 2 time steps, and we're trying to do a discrete Fourier transform. The DFT matrix exactly is this matrix. Therefore, and we can generalize it to any t types of inducing points that is written in a t by t matrix. And this is the discrete Fourier transform, DFT. So as you can see that this something related to the imaginative numbers. Yeah, so here we basically generalize the 3 key ingredients to these 3 generalized factors. And now we can arrive at the final approach or final theorem, that is the harmonic kernel decomposition. So to give a very intuitive understanding of harmonic kernel decomposition, I'll talk about like what is a DFT. So discrete transform basically transform a time domain representation into frequency domain representations. Like for example, in this the red curve is the time domain signal, and using the discrete Fourier transform, the DFT, we transform it into frequency domain sinusoids, showing here in this blue curves. And we can use the inverse DFT to transfer it back. And in short, we can see what DFT does. It's trying to decompose the time domain signal into orthogonal sinusoids. And the orthogonality is because they have different frequencies. And the harmonic kernel decomposition and the 3 previous important components is actually a DFT applied to kernels. Instead of applied to signals, we applied it to kernel. And what it achieves is that it has the orthogonal kernel sum decomposition. So basically, it decomposes the kernel into the sum of multiple orthogonal kernels. That is HKD, or the harmonic kernel decomposition. And we're not touching many details about it for now. So basically, using the HKD, we can design this T types of inducing functions that are orthogonal to each other. So imagine that we have we use M inducing functions for every type of inducing functions. So we have T types, and each type has M inducing functions. So overall, we are using TM inducing functions. And interestingly is that this kernel matrix will be T by T block diagonal. So all the off diagonal terms are 0. Only the diagonal terms M by M are non-zero. And this is the harmonic variational Gaussian process because we can use it as inducing points in our variational GP. This is HVGP. So compared to SVGP, it's very similar because they both just trying to optimize the elbow. They support stochastic midi-batch estimation, so they can do large data sets, and they are applicable to high-dimensional inputs, and they can train the inducing points as well because the inducing function depends on the location of inducing points, so you can train it as well. So it's very similar to SVGP, and it's also better than SVGP because it's orthogonality issue or orthogonality phenomena. We can see that we can use more inducing points because of this smaller computational cost. And finally, because the orthogonality between these T types of inducing points, it can be very easy to be parallelized because the operations between these different types of inducing points are basically irrelevant. So you can just put the operations of one type of inducing points into one device and just parallel them. So it can be parallelized very easily. In short, HVG achieves is the substantial reduction in computational complexities. So in original SVGP, if you use Tm inducing points, that will be T cubic and cubic. By using HVGP, it will be much smaller. And besides that, this is very fast in terms of computations. It is also accurate. We can show that it achieves a high fidelity GP posterior approximation if the transformation is chosen properly. So here I'm showing a toy example where I'm using a GP to do the MNIST classification problem. And for this, there are several curves. So for two figures, is rather than the training loss, the test accuracy, I'm showing 4 curves. One is SVGP using 100 inducing points, SVGP using 400 inducing points, and HVGP using the negation transformation, HVGP using the flipped transformation. So, and we have 4 groups, and each group has 100. So overall, we are using 400 inducing points. As we can see, because the MNIST classification problem is slightly altered to have some symmetry between for flips. And we can observe that if we use a transformation properly as flip, the HVGP performance actually matches or even slightly better. I'll say matches the SVGP with 400 each points. Therefore, it enjoys the computational savings and is also very, very accurate. That is HVGP. And finally, I'll just show some experimental results. So firstly, I'll say that apparently it enables us to using more inducing points. So here is an example of our using GP to fit the elevation data over the Earth. And in the left, I'm showing a SVGP where we can use 1,000 inducing points or maybe 2,000 at the most. And the right-hand side, I'm using HVGP with 13 groups, each group with 1,000 inducing points. So overall, I'm using 13,000 inducing points and maximize the elbow. That is not seen before. And we can see by using more inducing points, it fits the data with more details. So of course, when we're using more inducing points, we have better predictive performances. Like here in the left figure, I'm showing an example where I'm doing a regression benchmark comparing the SVGP with M inducing points. Here M is 1024, 2 M inducing points, and HVGP with 8 groups of M or 2 M inducing points. As you can see that using more inducing points gave us better performance in terms of this negative log likelihood. So nevertheless, as I mentioned before, is that HVGP can be easily parallelized. And if we do the parallelization, we can see actually using 8 groups of M inducing points has only a small computation increase compared to SVGP using M inducing points. And using 8 groups of 2 M inducing points has only a small computational increase compared to using 2 M inducing points in a standard SVGP. So it can be easily parallelized, it's fast, it's also accurate. And finally, I'm showing that, so a very good, why SVGP is so popular is that because it enables flexible model designs. It's applicable to Gaussian likelihood, to any arbitrary non-conjugate, non-Gaussian likelihood. It can be stacked together to be used in deep Gaussian processes, to convolutional Gaussian process, and to be used in deep convolutional Gaussian process. So it's a very widely applicable. Similarly, HVGP is similarly applicable, just the same as SVGP. So wherever you can use SVGP, you can use HVGP. And here I'm showing an example where I am comparing HVGP with 2 groups or 4 groups with SVGP. And in terms of safe-return classification in a deep convolutional GP. So basically, we achieved, when we using more induced points, we achieve better performance. And we achieve state-of-art performance in terms of safe-return classification in GP models. And as you can see, the running time is also it's not increased drastically. And that's basically is this product about this product. And also it raises several interesting future directions. Is that, as I mentioned, that to apply HVGP, we need to find the transformation. For example, if you have an RBF kernel, we can use a transformation as a rotation. And the transformation, it actually is critical to the performance of HVGP. So it's intriguing to think about, can we do transformations over adaptive manifold that is more structured? And also transformation beyond cyclic groups. So in this, previously we talked about that cyclic transformation basically means that we apply transformation by t times, it gets back to the original point, but we can see it as a cyclic group of t elements. So it's actually could be generalized to transformation that is non-cyclic groups, maybe any polyhedron group. And lastly, that the harmonic kernel decomposition is an alternative representation of the original kernel. So based on that, you might be able to design more expressive kernels using the harmonic kernel decomposition to have this kernel learning approaches. And that's finished this first product. In a take-away message is that we introduced HVGP that uses orthogonal interdomain induced points and achieves substantial computational improvements. And yeah, I think that if it might be a good time step to answer questions if you do have some, or I can just continue.
Yeah, Shengyang, I have a question. So yeah, this is super cool, and I think that it's a really clever idea, and the computational speedups are yeah, like pretty remarkable. I think what I'm still trying to wrap my head around is like, could you imagine like what the failure case of this method would be? So like I'm trying to understand when this could like what information is being thrown away when you have for example, when you are constraining your inducing points to have this type of structure.
Yeah, that's the fantastic question. So actually I skip it during the talk. So HVGP doesn't work forever. So it has some caveat because here I'm mentioning that the high fidelity GP approximation relies on the assumption that if the transformation G is properly chosen. So basically, the HVGP basically maps the original inducing points using under the orbits of the transformation G. And we would like to make sure that when we apply G, the transformed data point still lies on the data manifold. So here is an example where I didn't mention that if we use a bad transformation, for example, here I'm showing HVGP with negation, the transformation as negation. But the negation actually is a bad transformation for this flip MNIST, because if you negate image, the resulting point will not be an MNIST image anymore. And as we can see, if we use a very bad transformation, even if we use more in this point, the performance only can match the standard HVGP with 1,000 data points. Therefore, basically my answer is that we need to choose a good transformation. And if you have a good transformation, we have a lot of good benefits. If we cannot find one, then there will be issue. And that's also why I talk about transformation over adaptive manifold, so that if the data manifold is not structured, it's quite bad, it's quite messy. If we still want to apply HVGP, we might need to have some adaptive manifold learning approach. Yeah.
I see. Thank you. In the interest of time, maybe we'll have plenty of time for questions after the talk, but just in the interest of having the main portion of the talk end on the hour, it might be good to move on to the second half.
Yeah. Yeah. Maybe. Yeah. I think maybe we can start if you don't have more questions. So yeah, I'll talk about the second product, basically trying to understand finite-wise neural networks as interdomain inducing points. So first, I'll briefly mention about existing kernel perspective on neural networks. So recently, people have been very excited about understanding neural networks using kernel approaches. And generally, the first kind of understanding we have at present is that infinite-wise neural networks and initialization are Gaussian processes, because when we do the integration using the central limit theorem, it essentially behaves like a Gaussian process prior. And that dates back to the study of NEO at 1992, and recently has the resurgence. This Gaussian process is usually called the neural network Gaussian process. And also, more popularly is that people find that infinite-wise neural networks at training are Gaussian process, or say the neural tangent kernel actually governs the training dynamics of infinite-wise neural networks. And they use this technique to understand, to prove the global convergence of neural networks. So they achieved a lot of successes, but some caveats of them are apparent as well, is that they relies heavily on the infinite-wise assumption. So this approach only hold when the networks are infinite-wise. And there are some works that try to understand finite-wise, but basically the assumption that they approximate the infinite-wise network very well. And because they relies on the infinite-wise assumption, it ignores the importance of individual weights. So you cannot understand the importance of single weights. And finally, their performance fails to match standard neural networks of a determinate neural network with the standard training, standard optimizer approaches. And people are trying alternative ways, trying to measure performance. And this paper, we're trying to give an alternative kernel perspective to understand finite-wise neural networks. To start with, I'm trying to show a simple diagram of a two-layer neural network and the predictive mean of a sparse GP. So what is a two-layer neural network's computation can basically be written in such form. So we have the weights W in the first layer is multiplied with the input vector X, passes with the nonlinear activation, and finally multiplied with the weights in the second layer, A, and we get output. That is a two-layer neural network. And the predictive mean of sparse GP can be written in such form. So we have a list of inducing points, Z. We have the input vector X. We compute the kernel value between Z and X, and we multiply it to a vector A. This is the predictive mean of sparse GP. In particular, in sparse GP, the vector A will be KZZ inverse times mu. Mu is the predictive, is a mean, posterior mean of the inducing variables. So if we put them together, we wonder, do this seem very similar? Actually, they are not only similar, they can be shown to be equivalent. And that is what we are showing now. So in particular, previously in the background section, I introduced the interdomain induced points and the variational Fourier features. So the first project talked about interdomain induced points, and this project defines variational Fourier features. In particular, I define several variational Fourier features, Zi. Zi is a function mapping from X to sigma Wi transform X. So basically, as we can see, Zix basically is the activation value of the ith hidden unit of this two-layer neural network when the input is X. So if Zi is the inducing function of this variational Fourier feature, we can augment the kernel to compute the kernel value between X and Zi. In particular, the intriguing property of variational Fourier features is that the augmented kernel value between X and Zi is the evaluation of Zi on X. That is exactly the activation value of the ith hidden unit. And similarly, we can compute the augmented kernel value between any two variational Fourier features, Zi and Zg. So, and basically they can be computed in the RHS inner products between the two functions. But more interesting is the formula of the kxzi is the cross kernel value between the input and the inducing function. Now, if kxzi equals sigma w transpose x, we will have the equivalence. Therefore, if we use variational Fourier features as these inducing functions z, then this predictive mean of sparse GP will be exactly the two-layer neural network. Or in turn, we can see that a two-layer neural network is the predictive mean of a sparse GP under this variational Fourier features. So this gives us new interpretation of finite-wise neural networks. So firstly, we can see that each activation function, so it's a function, depends on the weights related to that hidden unit or related to that unit, can be seen as the interdomain inducing point P of Z and or a variational Fourier feature. Because each activation function is an inducing point, then the width of this neural network or the number of hidden units equals the number of inducing points. So if you have a neural network with 100 hidden units, this basically becomes 100 inducing points. And finally, more importantly, the main message is that a two-layer neural network becomes equivalent to the predictive mean of a variational GP. And if we look at, so this is understanding the finite-wise neural network. If we try to look at the variational GP, we can see the variational GP is that the fx has a Gaussian distribution. The mean is this neural network, and with some particular variance. That is variational GP, and in particular, its performance matches the standard neural network because the standard neural network is exactly the mean of this variational GP under this interpretation. So, but we have this interpretation, but how is this useful? And here I'm showing an example about why this is useful. In particular, what I'm trying to do is that I can extract direct uncertainty from post-trained neural network. So what does this mean? So firstly, what's the post-trained neural network? It means that we train a neural network by standard backprop. So this is the standard deterministic neural network. We train it using your favorite optimizer like SGD, Atom, using your favorite objective, maybe cross entropy or VDK, learning rate schedules. And finally, we arrive at a deterministic neural network. That is the neural network starting with, that's the post-trained neural network. And we have this interpretation is that every hidden unit is an interdomain inducing point. So if we can understand this neural network as the predictive mean of a variational GP, we can try to see what is the variance of this variational GP. We can compute it or approximate it actually. So the variance of the variational GP can be written in such form. Basically, it is the Nernst approximation error. We're using Z as the inducing variables. And so here, of course, Z is a variational Fourier feature we defined before. And we also have the inducing variable variance, that S is the variance from the induced variables. So usually the second term can be small, and we can approximate it as the Nernst approximation error. We know that all these terms can be computed because if you have the kernel K, maybe a neural tangent kernel corresponding to the network architecture, and KZX is exactly the activation evaluated at X, and KZZ will be the RKHS inner products between inducing functions. So we can compute the variance of the sparse GP directly from the post-trained neural network. We do not need to do any fine-tuning, do any other training procedure. Only if we have the post-trained deterministic network, we can compute the variance, and that is named the direct uncertainty by me, actually, yeah. And in particular, in this project, we derived analytic expressions of the kernel augmented kernel values between inducing functions for two-layer neural networks. Here, Z and ZG are like say the activations of this two-layer neural network. So we can show this in some real example. So here in the left, I'm showing a two-layer cosine neural network. So the black dots are the training examples. I use a two-layer network with cosine activation and fit it on the training data. We can see the predictions. So note that this is the deterministic neural network, and only what do we know about the network is only the weights. So given this deterministic trained network, we can directly generate uncertainty using the previously mentioned procedure that is shown here as a shaded area. As we can see, the generated uncertainty is quite reasonable. It's kind of small in regions with training data and grows larger in regions far away from training data. And we also show this in a separate example where we have a two-layer neural network with the ERF activation instead of cosine, and it's the two inputs classification problem. And here the solid line is a predicted mean from this deterministic neural network. And the dashed line are the confidence interval by one standard deviation that we directly generated using the interpretation. So till now, it sounds very promising, but what we have only is about two-layer neural networks. So what about deep neural networks? So here is my current argument is that a deep neural network also corresponds to a variational JP. In particular, this is in contrast with a recent paper from Tutorial et al. And also, if a deep neural network corresponds to a variational JP, what are the inducing variables? Actually, each hidden unit at the second last layer is the interdomain inducing point. As I show in here, imagine that we pass X through a giant neural network, and Z1, Z2, Z3 are the final three hidden units. And these three nodes are the three inducing functions that I will use for this variational JP. And similarly, and if we use this as inducing functions, then this neural network, the whole computation will become the predictive mean of a variational JP. And we can do the similar things as well. But the caveat is that the analytic expression of KZIZG will be generally intractable because the deep neural network computation are so complex. It's hard to compute their RHS inner products exactly. And we need to turn to some approximations. So what are the future directions along this line? We know that, so currently the direct uncertainty from post-trained deep neural network is quite appealing to me because imagine that you train a ResNet and you can directly generate uncertainty out of it. And that is very interesting. And we can also use this using this interpretation to give generation bound for neural networks. For example, landmark paper from Birkin et al. Shows that, like basically mentioned the background, showing that you can give a generation bound if you know the RHS norm of this function. And this using our interpretation, you can similarly do that. And because of that, you can also have alternative regularization beyond L2 VDK, but maybe using RHS norm in VDK in neural net training. But they are all very good future directions, but they all based on the same obstacle is that the first obstacle to overcome is to have accurate and efficient approximations of the kernel between inducing variables, KZIZG, which essentially is the RHS inner product between these two functions. Yeah, and a takeaway message for this project is that we use this interdomain in these points interpretation to see that finite-wise neural networks is a variational JP or is a predictive mean of variational JP, and you can extract the predictive variance of this variational JP as well. Yeah, and this finishes this second project, and we have some end remarks. So this talk covers two projects, and basically what they tell us is that if you have careful design of interdomain points, you can bring substantial computational savings in variational Gaussian processes. And also, interdomain points also provides a promising direction to understand finite-wise neural networks. Some related references are shown here for your information. Yeah, and that is the finish of my talk. And I think probably it's a good time to answer some questions.
All right, everyone, let's thank Shengyang for an awesome talk. So we'll now move on to the question, answer, and discussion period. So we will have a period of questions that will be live streamed, following which we will conclude the live stream for those that prefer not to be recorded, and we will continue discussion on Zoom. So If you have a question for our speaker, please use the chat or the raise your hand feature to ask questions, and we will unmute you to speak. I will go ahead and start with the question of my own, actually, while we're waiting for others. So with the second part of the talk here, to get these uncertainty estimates out of neural networks. So I think that again, this is really exciting and appealing. Here, the uncertainty estimate that you would get would so here that will depend on, I guess it would be the choice of kernel that is induced by the choice of non-linearity that you're using here in the two-layer neural network. Is that correct?
Yeah, exactly. That's the very key point, because when we have in these neural networks, we have vastly different, infinite amount of choice of a kernel that we can choose. But so choosing the kernel definitely influence the final performance a lot. And so in my current argument is that we should choose a kernel as a neural tangent kernel, because the association of this, because the theory of neural tangent kernel, when we have infinite wide neural networks, the neural network actually behaves like kernel ridge regression, and there's a neural tangent kernel. And imagine that if we see it in this inducing variational inducing points under interpretation, if I have an infinite amount of inducing points, then this variational GP actually should become exact. And what is that? That will be neural tangent kernel. So therefore, the kernel K I'm assuming here is a neural tangent kernel corresponding to the infinite wise network, infinite version of this network. And for example, here I'm using a neural tangent kernel for this infinite wise cosine network. Here I'm using an infinite wise, the neural tangent kernel for the infinite wise ERF neural network.
Mm-hmm. And I guess a related question there. So right now there's the theory that you developed is for two-layer networks, and I see the or I guess like one hidden layer neural networks, and I see how this would in fact correspond to with this inducing point framework. When thinking about deeper neural networks, is there any intuition that you have for how this could be fit into an inducing point framework, or would that would then the correct choice of model be something more like a deep Gaussian process, or would there be something like a different way of viewing this as within the context of inducing points for Gaussian processes?
Yeah, that's very good question actually. So currently, because I'm mentioning here as an argument, because actually I'm still working on it, so I'm 100% sure about this, so I call it an argument. So as you mentioned, that actually there are two ways trying to understand it. One is that we can see a deep neural network as a stack of multiple two-layer neural networks, and you can see each two-layer neural network as a Gaussian process. So essentially, this deep neural network becomes a deep Gaussian process. And this is what is shown in this paper I referenced here, recently published by Neurips. So, but when I say it, but it's actually have some difficulties that when I try to work on it, because actually, if you're trying to transform a deep neural network into stacks of two-layer neural networks, there will be actually some parameter, like sharing parameters that, for example, a two-layer neural net, deep neural network of L layers has L layer L weight matrix, but the deep neural network with L two-layer neural networks actually has two L weight matrix. So you really have this parameter like over-defined issue in this deep neural networks in the deep Gaussian process interpretation. And why would I prefer the deep neural network as a variational GP, a single variational GP, also is related to the understanding, related to the theory of neural tangent kernel, because this theory of neural tangent kernel already shows that even if we have a deep neural network, if it's infinite wise, you still converge to a kernel ridge regression instead of some deep kernel ridge regression model. So therefore, when it's finite wise and we understand it as the variational GP, variational model, I think that understanding as the variational GP will be more consistent to it. And it also directly, so all previous analysis and the result can be directly actionable as long as we can compute KZIZG. So as long as we can compute the KZIZG for this complex ZIZG induced functions, everything else will be the same. So no other difficulties will be raised. And that's why I favor this argument right now. Yeah.
I see. And as far as, are there any methods that you have right now for approximating that, or could you use like any sort of like, Monte Carlo integration or quadrature or something like that to approximate KZIZJ when an analytic expression is not available, or is it too high dimensional for that?
Yeah, so actually, currently I have some ideas. So firstly, that I can give an upper bound for KZIZG that can easily computed, but that upper bound increases exponentially with layer. So that is actually a vacuous upper bound that's useless. And more practically, as we mentioned, that is actually we can estimate that. In particular, if we're trying to estimate the architectural inner products of two functions, imagine that we evaluate the function at a lot of locations and we get two vectors. Then this architect's norm can be estimated by this two vectors, for example, f and g, by f with times the kernel matrix inverse with g. So this can be, it's proved to be, it's shown to have a probability convergence to the true architectural inner products in probability. But this also has a problem is that if the number of evaluated points are large, the computation will be n cubic, will be like n is the number of points to evaluate. But maybe there might be some like fast approaches for the conjugate gradients to evaluate, because essentially we are trying to estimate is the matrix inverse vector product, and there might be like faster solver for that. And yeah, that is something that I haven't touched yet.
Interesting, thank you. All right, at this point, I think we will conclude the live stream. But before this, I want to thank everyone on YouTube who joined in. Thank you for joining us today. And as a reminder, we have another seminar coming up next week, I believe. Yes, we do have one next week. Just wanted to make sure that I wasn't leading people astray there. So please check out the schedule on our website, and please feel free to join us next week.